The objectives for this module are: define support vector machines, discuss the working of support vector machines, understand linear separators, discuss margins, explore nonlinear support vector machines, understand kernel functions, and discuss the support vector machine applications. Support vector machines. Support vector machines is a supervised machine learning algorithm that can be used for both classification and regression challenges. So support vector machine can be used both for classification and regression problems. Support vector machine is a discriminative classifier formally defined by a separating hyperplane. So basically it is a discriminative classifier that divides categories or classifies data according to separating hyperplanes. In other words, given labeled training data in supervised learning model, the algorithm outputs an optimal hyperplane that categorizes new examples. So basically it can be also used in clustering thus because it categorizes new examples or new data according to the training data which is fed in supervised learning model time, training time I mean. Regarding feature spaces, we may separate data by mapping to a higher dimensional feature space. The feature space may have an infinite number of dimensions. So we will see how we map from low dimensions to high dimensional feature space. So this helps us in better clustering the samples. Working of SVMs or support vector machines is shown here. Here we have three hyperplanes A, B and C, and hyperplane B is the right or the correct hyperplane that distinguishes the two categories of red circles and stars. Stars are on this side and red circles on this side. So basically if we draw A, you see A here, so it will have few reds on this side which are not desired. If we take C for example, it has reds on both sides and half of the star has both sides also. But B is the hyperplane which is the divider of the two categories which divides them both correctly. So B is the right hyperplane to choose. In this diagram we see three hyperplanes A, B and C and all are correct, but we choose C because it has the maximum margin on both sides. So this side the distance from this class is this much and from this class is this much. So both sides taken individually it has the maximum distance, while A has a not has that much distance here on this side red side, and B does not have that much distance on the star side. So both sides distance is maximum with C, so distance is termed also as margin. So maximum margin classifier is taken as the best hyperplane, which is C here. In this diagram here, A is the best hyperplane, but B has a good margin from both sides. This is the condition of impurity into the class. So impurity is caused, for example, by this star variable here, which causes this the best classifier A to be not that much good. So because the margin of B is equal on both sides, I mean the greatest of A and B. So this is the case of impurity, and to deal with that we use slack variables that will be discussed in further topics. So now we will discuss how we transform low dimensional data to high dimensional data so that they can be separable. The example is given in this diagram where both classes are not linearly separable. So if we draw a line or a curve, we don't be dividing both classes correctly or classifying both classes correctly. So to apply SVM, we will have to make these classes linearly separable. And for that we use kernel technique. Using kernel technique, the data dimension can be increased and it can be made linearly separable. So it increases the dimensionality of the input data and maps it to a higher dimensional data or graph. So we can apply SVM on that, and with the help, this is done with the help of kernels. So if we applied the kernel function on the previous slide, we will get this graph here, which is linearly separable like this. So kernel functions help us to map lower dimensional data to higher dimensional data, thus helping to apply SVM on the data. Linear separators. Perceptron revisited. In the case of linear separators, binary classification can be viewed as a task of separating classes in feature space. So here the perceptron algorithm was sigmoid of WTX plus B, and where WTX plus B is equal to 0 identifies this classifier here, this hyperplane, and if WTX plus B is less than 0, the data falls in this side, otherwise it falls in this side. So that is the working of linear separators with perceptrons. Moving forward, we see the large margin linear classifier where we know that WTX plus B is equal to 1 is for the class which have on the left hand or on the positive side of the curve, and WTX minus plus B is equal to minus 1 is for those class which is on the other side. So the margin width is given by M, which is equal to x minus into n, where x plus and s minus are the x values of the support vectors for each of these classes. So I'll discuss what support vectors are in coming slides, and which is also given as, and is also written as w by w plus modulo, which can be further simplified to T2 by w plus, I mean 2 by modulo w. So this is the equation for M. I'll not go deeper into the maths involved, but this is the equation. So now we see the explanation for the previous slide. So these two green dots are the support vectors for this green dots class, and this white dot here is the support vector for this white dots class. So basically we draw perpendicular from the support vectors, and from here to here, and other perpendicular where it cuts those perpendicularly is the hyperplane. So hope this is clear. Here n is this width from one class to the other class, and m is the margin. Here margin is the width of the linear classifier, and support vectors determine how the margin is made. Now we discuss how we draw linear separators. So the problem is to specify which of the linear separators is optimal in images below. So first we have the data set on this slide. We'll see the separators in coming slides. Data set is this, the pink dots and the blue squares. So these two linear separators are given in this slide. So which one of the best is the question. So the answer is this one, because it has equivalent margin from greater margin from both the sides, whereas in this side it is not less margin on this side. So we discussed the algorithm to find the best linear separator. So given the set of data points, we find the closest point in convex hulls. So basically convex hulls form out of this pink dots as like this, and out of these blue squares like this. So these two convex hulls have the closest points as this two, this and this. So we find them. Next we draw a plane to bisect the closest points. So this is the blue line, which is the plane that bisects the closest points. So assuming all the data is at a distance larger than 1 from the hyperplane, the following two constraints follow for a training set of xi and yi points, where wt xi plus b greater than equal to 1 if yi is equal to 1, and wt xi plus b less than equal to minus 1 if yi is equal to minus 1. Hope this is clear. For support vectors, the inequality becomes an equality then, since each example's distance from the hyperplane is r is equal to wtx plus b by w, margin is rho is equal to 2 by mod of w. Then finally we can formulate the quadratic optimization problem, which is find w and b such that dou is equal to 2 by modulo of w is maximized and for all xi yi points, and wt xi plus b greater than equal to 1 if yi is equal to 1, and wt xi plus b less than equal to minus 1 if yi is equal to minus 1. So we need to maximize the margin or dou. That is our goal in this algorithm. So a better formulation can be find w and b such that phi of x is equal to half of wt into w is minimized and for all points xi yi, and where yi into wt xi plus b greater than equal to 1. So the solution for the above problem is this in the final line here. W is equal to summation alpha I yi xi and b is equal to yk minus wt xk for any xk such that alpha k not equal to 0. So that is the solution for this problem. So in the previous formula, each non-zero alpha I indicates the corresponding xi is a support vector. So where alpha I is non-zero, xi will be a support vector, then the classifying function will have the form fx is equal to summation alpha I yi xi transpose into x plus b. Notice that it relies on an inner product between the test point x and the support vectors xi. So xi is the support vectors here for which we are taking summation, and x is the new test point for which we are calculating fx. Also, solving the optimization problem involves computing the inner products xit transpose into xj between all training points. So for the optimization problem, for optimizing this model, we have to calculate inner products xi transpose into xj, where xj is the training point involved, and we have to do this for all the training points. Now we discuss margins. First one is classification margin. Distance from example data to the separator is r is equal to wtx plus b divided by modulo of w, where x is the training data. Data closest to the hyperplane are support vectors as we have discussed earlier. Margin dou of the separator is the width of the separation between classes. So dou is the separation width between classes. Maximum margin classification. According to intuition and theory, maximizing the margin is good, implies that only support vectors are important. Other training examples are ignorable. So when choosing support vectors, we choose the best ones so that our margin is maximized, which is logically okay. And for so other training examples are ignorable in this case. Now we move on to statistical learning theory. Misclassification error and the function complexity bound generalization error might occur. So maximizing margins minimizes complexity and eliminates overfitting. So if you maximize the margin, it minimizes the complexity involved and eliminates overfitting, because it is the case in support vector machines that if we choose the best support vectors, the overfitting is avoided, and solution depends only on support vectors and not on the other attributes like number of attributes. So this we have discussed earlier as well. We choose the best support vectors so that we can ignore other training points. Margins and complexity. Skinny margin is more flexible, thus more complex. So if we have a thin margin, it is more complex because uh, we have to train it more in order to achieve the best separator. So it is more computationally more complex. So contrary to skinny margins, fat margins are less complex. So given a thick margin, it is computationally less efficient to, I mean more efficient to calculate that from a case of skinny margins. Soft margin classification. What if the training set is non-linearly separable? We introduce slack variables epsilon I which can be added to allow misclassification of difficult or noisy examples. So for example, this red circle is in the blue dots area and this circle is in the red dots area. So this case is not linearly separable. So we can introduce epsilon I or slack variables to allow misclassification of difficult or noisy examples. So these can be considered as noise. So we can allow epsilon I to allow misclassification of these. So the effect of value of C or coefficient of slack variable is discussed in this slide. So the large value of for parameter C will result in this graph here, and small value for parameter C will result in this graph here. So it should be an optimal value in between large and small. Basically, if it is large value, then it will be a very close margin, and small value might not classify I mean these types of circles at all. So we discussed soft margin classification mathematically. So this is our old formula here. So the new formulation incorporating slack variables is find W and B such that psi of W is equal to half of W transpose into W plus C summation epsilon I is minimized for all training points such that yi into W transpose xi plus b greater than equal to 1 minus epsilon I and epsilon I greater than equal to 0 for all I. Hope this is clear. Parameter C can be viewed as a way to control overfitting. So C is our tuning parameter and can be viewed as a way to control overfitting. So the solution to the short margin classification problem is given in this slide. So the dual problem for short margin classification is this. The solution for dual problem is given by this here. So neither slack variables psi, epsilon I or nor their Lagrange multipliers appear in the dual problem. So this is the dual problem in which epsilon I is not mentioned. They don't appear. Again, xi with non-zero alpha I will be support vectors as in the previously discussed. Solution to the dual problem is this one. Hope this is clear. So finally, we don't need W or B explicitly for classification. So we can write fx is equal to summation of alpha I yi xi transpose into x plus b. Soft versus hard margin support vector machine. Soft margin always has a solution. So even if hard margin does not classify the target test value properly, soft margin will always, on the contrary, classify it properly. Soft margin is more robust to outliers. As discussed, if any outliers are there in one class, it will short margin is more robust to classifying it, and short margin results in smoother surfaces in the non-linear case. Hard margin does not require to guess the cost parameter, and it requires no parameters at all. But sort margins requires cost parameter, and we require to tune it as well for our model. So we give an overview of the linear support vector machine as discussed. The classifier is a separating hyperplane. Most important training points are support vectors. They define the hyperplane. Quadratic optimization algorithms can identify which training points xi are support vectors with non-zero Lagrangian multipliers alpha I, both in the dual formulation of the problem and in the solution. Training points appear only inside the inner products. So this is the final formula where training points appear inside the inner products. Now we discuss how we move to non-linear from linear support vector machines. Non-linear support vector machine allows the algorithm to fit the maximum margin hyperplane in a transformed feature space. So we discuss briefly how we transform from linear space to multidimensional space so that we can fit a maximum margin hyperplane in that. The transformation may be non-linear and the transformed space can be high dimensional. Thus, though the classifier is a hyperplane in the higher dimensional feature space, it may be non-linear in the original input space. This is clear, I hope. So basically, since the classifier is a hyperplane in the higher dimensional feature space, it might be non-linear in the original input space that was given to the model. Datasets that are linearly separable with some or little noise work out great. So if datasets that have some or little noise that are linearly separable work out great. But what will we do if the dataset is just too hard or having too much noise? How about mapping data to a higher dimensional space as below? So if you map this upper input data to a lower data space as shown in the below diagram, we have mapped this into this, which is a higher dimensional space. So all the data points are determined by this, and then we can draw the hyperplane like this that will classify the data. So when we look at the hyperplane in the original input space, it looks like a circle, which is a non-linear case. So finally, we discuss the working functionality of transforming to non-linear SVMs, which is kernels. You may use kernel functions to implicitly map to a new feature space. Kernel function is defined as k x1 x2 element of R. So given two vectors x1 and x2, two variables I mean x1 and x2, we map it to a higher dimension using the kernel function k. So kernel must be equivalent to an inner product in some feature space. Suppose we are given x is equal to a and b vectors and x dot inner product w is equal to w1a plus w2b. Then we have the transformed kernel function after applying is theta x is equal to this much, where theta x into w is w1a plus w2b plus w3ab plus w4a square plus w5b square. Basically, it maps from x to theta x. So in this slide, we are given few kernel types which can be used for classifying support vector machines. So SVC is nothing but support vector classifier. So support vector classifier with linear kernel is shown in this here, and on the upper right quadrant we have the linear SVC or linear kernel, and again on the lower left quadrant we have SVC with RBF kernel, and SVC with polynomial kernel is shown in this one. We will discuss each of these kernels next. So kernel examples can be, first one is linear, where basically it is a vector z that is introduced, and final output is also linear. It can be polynomial, where z is a polynomial base function or vector, And it can be Gaussian, where the output formula is exponential of minus of x minus z whole square by alpha square, where each of z and alpha is a parameter that can be tuned. So the general idea to map feature spaces is the original feature space can always be mapped to some higher dimensional feature space where the training set is separable. So this is the original feature space, and this is the after transformation the final feature space looks like this, where it is classifiable and linearly separable. So nonlinear SVM mathematically is shown in this slide. The dual formulation problem for nonlinear SVM is this, where we have to find alpha 1 to alpha n such that q alpha is given by this and given these conditions, and the solution is fx is equal to summation of alpha I by I k of xi xj plus b. So k is that function that we have discussed previously, and optimization techniques for finding alpha I remain the same. So in this slide we can summarize neural networks versus support vector machines, where for example one trait is hidden layers map to lower dimensional spaces in neural networks, whereas in support vector machines kernel maps to a very high dimensional space. So basically in using hidden layers we can map to lower dimensional spaces, whereas kernel map to high dimensional space, so that we can fit a linear classifier in support vector machines. In neural networks, search space has multiple local minima, whereas in support vector machines, search space has a unique minimum. This will be clear with an example in future slides. And in neural networks, training is expensive because multiple hidden layers are involved, and in support vector machines, training is extremely efficient. But in both of these models, classification is extremely efficient, and in neural networks we require multiple hidden units and layers, whereas in support vector machines we use kernel and cost as the parameters for efficiency, and we have to tune them. Both of neural networks and support vector machines are good in typical domains, having good accuracy, but support vector machines are extremely robust in comparison to neural networks. Support vector machine extensions. We have seen that support vector machines can be used for classification, but as a special case, support vector machines can also be used for regression. We'll discuss that in future modules or example labs. And support vector machine can also be used for variable selection, boosting, density estimation, unsupervised learning cases, for example, novelty or outlier detection, feature detection, and clustering. So it can also be used for unsupervised learning in some cases, for example, clustering. The applications of SVM or use cases of support vector machines are given in this slide as examples. For example, we have speech recognition, we have text categorization, or in the medical field, we have cancer tissue classification, and so on. Now we move on to advantages of support vector machines. It works really well with clear margin of separation. So when we have a clear margin between the classifying clusters, we can use support vector machines. It is effective in high dimensional spaces. So when data is in high dimension also, it is very effective then. It is effective in cases where number of dimension is greater than the number of samples. So given the number of samples, the number of features is more, then we can use support vector machines. It uses a subset of training points in the decision function called support vectors. So it is also memory efficient. So fourth point says that we don't use the full set of training points. We only use the support vectors in memory. So it is very memory efficient. Disadvantages of support vector machines are discussed in this slide. It does not perform well when we have large dataset because the required training time is higher. It also does not perform very well when the dataset has more noise. That means target classes are overlapping. So when target classes are overlapping more and there is more noise in the dataset, it is very difficult to classify them. And support vector machine does not directly provide probability estimates. That means they don't provide probability estimates for the target output, and they have to be calculated using an expensive five-fold cross validation, and it is done using a method of Python scikit-learn library, which is computationally costly. So this is a disadvantage of support vector machine.